Now the next one is equation of a circle. Definition of a circle is locus of all the points which are equidistant from a given fixed point. So suppose the fixed point is center of the circle and it is at z0 and the fixed distance is radius r. So we have to write equation of a circle whose center is z0 and whose radius is r. Then we know that any point on this circle which is z will be at a distance r from z0. Now distance, it is given by mod, so it will be mod of z minus z0 and it must be equal to r. And this is your equation of circle. So equation of any circle whose center is z0 and whose radius is r will be given by this mod of z minus z0 equals r. Now say for example, suppose we have to plot this circle which is mod of z plus 1, it is equal to 1. Now we can write this as z minus of minus 1, it is equal to 1. So we'll represent a circle whose center is at minus 1 and whose radius is 1 units. So it will be this circle with center at minus 1 and radius 1 unit. Now there will be times where you'll be given points not only on the circle but on the inside or outside the circle. So one such case could be when they are going to write mod of z minus z0 is less than equal to r. In that case, it will represent all the points on or inside the circle whose center is z0 and whose radius is r. And if the question is mod of z minus z0, it is greater than or equal to r, then in that case, represent all the points on the circle with center z0, radius r and points lying outside this circle. Now here the question is, if the complex number z is such that mod z minus 1 is less than or equal to 1. So we have coordinate axis and then we have a circle whose center is at 1 and whose radius is also 1. So we are talking about all the points on or inside this circle. Now this point is 0 and this point is 2. Now the second one is mod z minus 2 equals 1. So this again is a circle with center at 2 and radius equals 1 unit. So all the complex numbers which satisfy both these conditions are this portion of second circle which lies inside or on this first circle. Now we know that maximum value of mod z will occur at this point. So this is maximum value of mod z. Now we drop a perpendicular. This is 1 unit. This is radius of this circle which is 1 unit and this length is 1 by 2. So we can find this d. This d will be under root of 1 minus 1 by 4 and will be root 3 by 2. Now we can find maximum value of mod z. Now this is d and this length is 1 plus 1 by 2 and will be 3 by 2. So this mod of z max square, it will be 3 by 2 square plus root 3 by 2 square. Now this is 9, 9 plus 3, 12. 12 upon 4 is simply 3. So the maximum possible value of z square is 3 and that's your answer to this question. So now we have studied that equation of circle is mod of z minus z0 equals r. Now another way to write this equation is we can square it. We can write mod of z minus z0 square, it is equal to r square, and we know that mod of z square is z into z bar. We can write this as z minus z0 into z bar minus z0 bar and it is equal to r square. Now we'll write this as z bar minus z0 bar z minus z0 z bar plus mod of z0 square minus r square equals 0. Now we take minus z0 as a which is some complex number. This is some b, which is real number. We can write this equation as z bar plus az bar plus a bar z plus b equals 0. So if in complex numbers, we have this equation which is z bar plus az bar plus a bar z plus b equals 0, then it will represent a circle whose center is at z0, which is minus a. So center of this circle will be at minus a, and its radius will be r square, which is mod of z0 square minus b, or we can write its radius will be under root of mod of a square minus b. So if we come across any equation which has z bar plus az bar plus a bar z plus b equals 0, then it will represent a circle whose center is at minus a and whose radius is under root of mod of a square minus b. So that is second way to write equation of this circle. Now third way to write equation of a circle is in terms of Apollonius circle, which is ratio of any point on the circle from two fixed points. If it is constant and unequal to 1, then the locus of this point will be a circle. So basically we'll be given this condition that mod of z minus z1 upon z minus z2, it is equal to k, and this k is unequal to 1. Now we have already studied in straight lines. If the value of k is 1, then in that case it will represent a straight line which is perpendicular bisector of z1 and z2. But if this k is unequal to 1, then in that case this equation will represent a circle. Basically we can simplify it to prove it is equation of a circle. So what we'll do is we'll square it again. We'll write mod of z minus z1 square will be equal to k square mod of z minus z2 square. Now this is z minus z1 into z bar minus z1 bar, and will be equal to k square z minus z2 into z bar minus z2 bar. Now we multiply it, we'll write z bar minus z1 bar z minus z1 z bar plus mod of z1 square, and it will be equal to k square z bar minus z2 bar z minus z2 z bar plus mod of z2 square. Now we take everything on the left hand side, then we can write 1 minus k square z bar minus z1 bar minus k square z2 bar z minus z1 minus k square z2 z bar plus mod of z1 square minus k square mod of z2 square equals 0. Now if this k it is equal to 1, then we won't have this z bar term. Then we can write this as a z bar plus a bar z plus b equals to 0, which is equation of a straight line. So if this k is equal to 1, then this equation it will represent a straight line. But if this k it is unequal to 1, we can write this as z bar minus z1 bar minus k square z2 bar upon z upon 1 minus k square minus z1 minus k square z2 upon 1 minus k square z bar plus mod of z1 square minus k square mod of z2 square upon 1 minus k square equals 0, which is z bar plus a bar z plus a z bar plus b equals to 0, which is equation of a circle. So basically if this k is unequal to 1, then this equation will represent a circle, and basically this circle it will be Apollonius circle. Now the fourth way to write equation of a circle is, if we are given n points of a diameter. So suppose we have a circle whose diameter is AB, which is given by Z1 and Z2. Then for any point on this circle P, we know that this angle in a semicircle is 90 degrees. So this triangle APB will be a right angle triangle, and if this P is given by Z, then we can write AP square plus BP square, and it must be equal to AB square. Now AP is distance between A and P. We can write this as mod of Z minus Z1 square, and BP is mod of Z minus Z2 square, and it will be equal to mod of Z1 minus Z2 whole square. So if we have any equation where we have mod of Z minus Z1 square plus mod of Z minus Z2 square, and it is equal to mod of Z1 minus Z2 whole square, it will represent equation of a circle. Another way to write the same equation is using argument. Now we know that this angle, it is 90 degrees. Now we can write angle between these two complex numbers, Z1 minus Z and Z2 minus Z. Then this angle, it must be pi by 2. So another way to write equation of the same circle is in terms of argument. So if argument of Z minus Z1 upon Z minus Z2, it is plus or minus pi by 2, then this Z will lie on a circle whose n points of diameter are Z1 and Z2. Now if we take only plus sign or only minus sign, in that case it will represent only a semicircle. And previously we have studied, if this argument Z minus Z1 upon Z minus Z2, it is 0 or pi, then this Z, it will lie on a straight line. So if it is 0 or pi, it's a straight line, and if it is plus minus pi by 2, then this Z, it will lie on a circle whose n points of diameter are A and B. Now another way to write the same equation is, now we know that its argument is plus or minus pi by 2. Now when the argument is plus or minus pi by 2, we know that this complex number, it must be purely imaginary. So we can write Z minus Z1 upon Z minus Z2, it is purely imaginary. So another way to write this equation is in terms of its real part. So if real part of Z minus Z1 upon Z minus Z2 is 0, then again represent the equation of this same circle. And if imaginary part is 0, then we already know it will represent a straight line. Now, seventh way to write this equation is in terms of its conjugate. Now we already know that Z minus Z1 upon Z minus Z2 is purely imaginary. And if the complex number is purely imaginary, then Z is equal to minus Z bar. So we can write Z minus Z1 upon Z minus Z2 will be equal to minus Z bar minus Z1 bar upon Z bar minus Z2 bar, and we can rearrange this as Z minus Z1 into Z bar minus Z2 bar, and it will be equal to minus Z minus Z2 into Z bar minus Z1 bar. Now we take everything on the left hand side, we can write Z minus Z1 into Z bar minus Z2 bar plus Z bar minus Z1 bar into Z minus Z2 equals 0. So this equation again will represent equation of a circle whose n points of diameter are Z1 and Z2. Now this eighth equation is not equation of a complete circle, but basically equation of a portion of a circle. Now suppose we say we have a circle whose chord is, say, AB, where A is given by Z1 and B is given by Z2. Now suppose this angle is alpha. Now we know that angle in the same segment is same. So this angle will be alpha irrespective of position of Z for this segment. For the other segment, it will be pi minus alpha. So if we write argument of Z minus Z2 upon Z minus Z1 equals to alpha, this equation again will represent a circle. Not a complete circle, but portion of the circle. That is the segment where this angle is alpha. So this equation will represent part of a circle except when alpha is 0 or pi. Now we need to find mirror image of this curve given by argument z plus iota upon z minus 1 equals pi by 4 in the line y equals x. Now what we are given is, we are given argument of z plus iota upon z minus 1 equals pi by 4. Now we can write this as tan inverse y plus 1 by x minus tan inverse y upon x minus 1, and it will be pi by 4. Now we'll use tan inverse A minus tan inverse B. We can write tan inverse y plus 1 upon x minus y upon x minus 1 upon 1 plus y plus 1 y upon x into x minus 1, and it is pi by 4. Now we'll take tan inverse to the right hand side. We can write xy minus y plus x minus 1 minus xy, and it will be equal to x square minus x plus y square plus y. Now this xy will cancel. We can write this as x square plus y square minus 2x plus 2y plus 1 equals 0. Now center of the circle is at 1 comma minus 1, and its radius will be 1 unit. So it will be this circle. This is 1 comma minus 1 and radius is 1 unit. Now we have to take reflection of the circle about y equals x line. So if we take reflection of the circle about y equals x line, now for this new circle, center will be at minus 1 comma 1 and radius will be 1. Now for this given circle, this point of contact is minus iota and 1, and for this circle contact is minus 1 and iota. So it has to be argument z minus iota upon z plus 1 equals pi by 4, and that's your option C. Suppose z is such that argument of z plus iota upon z minus iota, it lies between pi by 3 and 2 pi by 3, then locus of z is shaded region in adjacent figure. So we need to draw this shaded region. Now if we look at argument of z minus of minus iota upon z minus iota, and it is equal to some angle alpha, we know that this represents portion of a circle with chord passing from iota and minus iota and making an angle alpha. So what we'll do is, we'll draw the axis, and then we have 2 points, iota and minus iota. Now we consider a circle passing through iota and minus iota, then at any point z, this is z minus of minus iota, z minus iota, and this angle will be alpha. Now it says this angle, it must lie between pi by 3 and 2 pi by 3. So we have to draw this region, then we have to draw 2 circles. first circle in which it makes an angle pi by 3, and then this second circle at which it makes an angle 2 pi by 3. This again is iota, this is minus iota, this angle is pi by 3, and this angle is 2 pi by 3. So we need all the points z such that this argument, it always lies between pi by 3 and 2 pi by 3. That means we are talking about the region in between these two circles. So the locus of z is represented by this region within these two circles.